All right, folks, welcome to our second lecture on cellular automata. This time we're going to do 2D, so we're actually going to do Conway's Game of Life today. One of the things that I want to mention about the code that we're going to write later is that we're actually going to take the 1D version and we're going to modify it. And there's actually not a lot that we have to do. We already have a cell class. We already have a few different pieces, like looping through all of the sort of like rows and columns and stuff. We already have all of that set up, the grid pane, things like that. So it's relatively sort of minor changes to make. We're going to have to use a different set of rules. The 1D version has a specific set. We have to sort of think about it in a different way. But ultimately, there's not a lot that we have to do to get a nice working Conway's Game of Life. So let me talk specifically about that. The big thing about Conway's Game of Life is it's 2 dimensions. So rather than having that just sort of a single row representing our CA, we are going to have essentially a matrix. You can sort of think of it maybe like an image as well. Some of the code will be similar to the image processing stuff that we did as well. Now, the big thing here is, of course, it's more complicated than 1D. Every neighborhood is now 8 tiles, plus you have the center tile to make 9, and that leads to more possible configurations, but also more interesting or useful applications. This was created by John Conway in 1970. Martin Gardner, who was a mathematician, wrote an article in Scientific American that documented this game of life. And he sort of described it as recreational mathematics. He recommended getting out a chessboard and some checkers and actually playing it manually for yourself. Obviously, back in the 70s, computers weren't quite as ubiquitous as today, so you wouldn't necessarily have access to either download it or create it yourself. So this sort of game is something that when John Conway developed it, they didn't immediately put it on a computer. When he came up with the rules, him and I think some of his assistants were just coming up with sort of random rules, or at least rules that sort of sounded interesting, and they were working it out on a piece of paper. So the development of this was not something that was initially programmed. These days, it's more of a computational cliche. Use it for some example type stuff, and in sort of a CS1, CS2 style context. But it's actually still quite useful to demonstrate a lot of different concepts. And I think I mentioned this last time. I do Game of Life again in parallel computing. So even though it's sort of an upper division class, it's still very useful to talk about certain concepts in the parallel computing class. So let's talk about what this looks like. It's just a matrix, just full of ones and zeros. That's it. So instead of the line of cells, we have a matrix. Every cell has its value, 0 or 1. It's a game of life because 0 represents dead, 1 represents life. The neighborhood, of course, is 8 cells around some center cell that you pick. So you have sort of 9 cells total that you're dealing with. In the 1D version, we had 2 states and 3 cells. That gave us 8 total configurations. Well, if we do the same sort of calculation here, we have 9 total cells with 2 states each. That's 512 possible configurations of ones and zeros in that 9-cell region. So what we could do, of course, is we could do the same thing we did for the 1D case. I wrote like if and then else if, else if, else if, and I had 8 of those total. We could do that here. We could have 512 if else ifs. That's not very feasible. That's pretty much a waste of time, and it's prone to errors. So obviously we don't want to define 512 specific rules. So what we're going to do instead is we're going to reduce it down to about 5. You can sort of write it as like 3 if you're a little bit tricky. We're just going to define some general rules, the general look of the neighborhood, not the exact configuration, just what does the neighborhood sort of look like, rather than exactly where the ones and zeros specifically are. So here are the rules, and it comes down to sort of 5 here, but like I said, you can use some trickiness and you can sort of reduce it down to 3 if you're tricky. All right, so we have the death of a cell. So if the center cell, and so this is sort of references to the center cell here. If the center cell is alive, so it's a 1, then it dies, it changes to a 0 if there's overpopulation. So 4 or more alive neighbors. So in that group of 8 around the center cell, if there's 4 or more alive cells, then the center one dies. Again, sort of an overpopulation, not enough resources sort of thing. Or if there's loneliness, if there's 1 or fewer alive neighbors, not enough neighbors to continue living. That's sort of the idea here. So 4 or more alive neighbors, 1 or fewer alive neighbors. If you're alive, then you die. If a cell is dead, it comes back to life if there are exactly 3 alive neighbors. So the idea here that you should sort of start to see in these rules is that you just look at your neighbors. You look at sort of what the center cell is, and then you count the number of neighbors you have, and you decide what to do based on that number, not the exact configuration. It doesn't matter where the neighbors are alive, it just matters how many of them are alive. And then, of course, there's stasis. So if you are alive, you stay alive if there are 2 or 3 live neighbors, and if you're dead, you stay dead, anything other than 3 live neighbors. So that's the idea. You just look at those 8 neighboring cells and you count them up. And then, of course, you consider what you are, what the center cell is, to determine what happens. So the rules actually aren't that complicated. Way better than 512 specific rules that you have to code up. So I got a couple of examples here. So let's say we have a state like this. We count up our neighbors. So we are alive. We count up our neighbors. We have 1. This triggers the death rule. So we end up changing our state to being dead. In this situation, we're dead in the center. Count up all the live neighbors. There's 3. So there's a birth condition happening there. So it's relatively easy to sort of visually see, and this is why you can play this on a checkers board. It's very easy to do on a board like that, because you just have to look at each cell and count up its live neighbors. Now, there's a few notes to this, and there is sort of a coding complication that's going to come up a little bit later that I'll talk about. So for 1DCA, so the 1D version we did last time, we can stack up the generations. That's how we made that fractal triangle, that Sierpinski's triangle. But it's not viable for 2D. Instead, we turn it into a movie or an animation. Every single generation is a single frame of that movie. So instead of seeing all the generations at once, like we did in the 1D version, we see them over time. That's why if you watch Simulation of Game of Life, it looks like an animation or like a video or something. So that's the way that we're going to represent this, which means our JavaFX stuff is going to be changing every single tick. So we're going to need one of those sort of tick things to do as well, something for us to cause the board to change over time. So there's a few interesting structures that we're going to see as well. Some of them don't change. Some of them oscillate back and forth between 2 or potentially more states, and some move across the grid. So I want to show you a couple of these first, and I'll sort of point them out once we have it running. A block, for instance, though it's stationary. Now, all of these have names. People have been studying this for since 1970, so like 50 years, right? So all of these sort of possible sort of setups have names. So we have a block, beehive, loaf, boat. These will stay stationary. They're just going to sit there. They're never going to change generation to generation. That's because if you go through and do all of the possible rules here, you'll see that nothing here is going to change. The border around it is important, because if another cell were to come and become alive in the border, then it would start to change what the structure looks like. So the border that you see here is an important aspect of this. There's some that oscillate as well. So for example, we have the blinker. It starts as vertical here, and it's going to change to horizontal. We're going to see a whole bunch of these most likely. The toad here is going to sort of expand out and come back in. The beacon is going to sort of flash in the middle. So there's going to be some interesting stuff here for these ones that sort of oscillate. Then there's some that actually move across the grid itself. Things like a glider. Now it needs the space around it. That's why there's sort of 2 rows and 2 columns of empty space here, but it needs the space, and it'll sort of just move across the grid. It'll glide across the grid. Lightweight spaceship, we're probably not going to see. We're just going to start with a random, sort of a random board of ones and zeros. So unless you sort of explicitly make the lightweight spaceship, you're probably not going to see it. Because it needs so much empty space around it that and the sort of the randomness to create it. So probably not going to see this one, but this one also will it'll sort of change its shape as it's moving across the grid. So there's some really cool stuff that that we end up seeing here. Now let's go and let's go and start coding this up. It'll be sort of relatively straightforward. We'll get the board set up. We'll need some kind of function to actually run the simulation, because we're going to need to call that function from an action event, from our sort of tick, from our timeline tick. But overall, we're going to get this sort of working and displaying. So let's hop in, and I just have the previous one open. This is just the 1D one. I'm going to reduce the number of rows and columns. Maybe I'll just sort of make them about equal, make them about 100 and 100. Make them about 100 and 100. I still have the grid pane. I'm still creating a board. This time it's going to be 100, 100, and it's still filling them all up, in this case with new cells that are specifically this case is going to be sort of all empty, but we're going to make sure that we set up sort of a random state. So that means I don't need this anymore, this sort of setting the first cell to a 1. I don't need that. I'm going to keep the set of for loops here, but I'm going to change this back to 0 and put a -1 here like this. So I'm going to set this to those. And then I'm going to get rid of all of this sort of 1D stuff that we set up. So now I've got a grid. I've got a way to apply the rules to each generation. I might move this out. Think about it. Yeah, probably so. We should probably move this out to a separate function, because in here we're going to create our sort of tick. So let's do that. I'm trying to think of the best way here. We can probably just have the function take in a few arguments. We'll have it take in the board, probably the grid pane as well, and that might be all we need. We'll see. I'm sort of mostly doing this on the fly, because it's sort of relatively straightforward for what we need to do. So let's write a quick function here. Say public static. Let's see. This will be void, and let's call it update game. So we'll send in a cell array, a 2-dimensional cell array that I'm just going to call board, and we will send in a grid pane. Pane P. Good enough. So this sort of setup where we apply the rules, we're going to put that down inside of here. Now we might have a couple other variables up top here. That's fine. I have the sort of rows and columns here. We need to make sure we use the board to generate that, or to get that. So I'm going to say board. Actually, let's keep this as rows here, and let's actually create a variable for it. Int rows. The number of rows is the board dot length, and we know that our board is going to be square. So the number of columns in each row is just board 0. I'm picking the first row, and I'm getting the length of that first row. So I'm just basing it off of what our board actually looks like for the rows and columns. All right, so let's go set. So this is just sort of getting this sort of ready to go. Along with our pane and stuff. So let's go up here and let's set up the randomness. So in our setting up of the cell array, let's see, we'll use a random number generator. So let's generate one outside. So I'm going to create a random rand equals new random. And in here, we need to make sure that this gets imported. And then after we create each individual cell within our board, let's make sure that, let's actually do this in a separate set of loops. We could do it here, but I want to make sure that I don't change the edge. So they want to do the same thing with the edge, with the edges. So the first row, the first and last column, and the last row. I'm going to do the same thing we did with the 1D version. Make it so those are just sort of fixed at 0. So that's why down here in our update game, should be a 1 here. We're not going to update that first row and last row and first row and last column. We're not going to update those. Those are just going to be set to 0. It's just sort of our region at the corners, so we don't really have to deal with any of the sort of edges in our grid. So let's just do a separate loop for this. So we're going to say give the board random values. So it's going to be the same style of loops that we have here, but we're going to use the sort of beginning and ending versions like they are in the update function that we just wrote. So we're going to go from 1 to rows or columns minus 1. Then I'm going to generate a random number. So I'm going to say int, I'm just going to call it r. This will be rand.nextInt, and the bound here is going to be, I'm going to put 2, so that we generate either a 0 or a 1. Remember, when I put in a bound here, it doesn't include that bound. It's exclusive. So this is generates a 0 or 1. So it's going to generate a 0 or 1, and then all we have to do is say board ij dot set state r. So this gives us our random board. Now what we can do right now is we can run this and we can check and see if it looks like what we expect. So if I run this now, there we go. There is our random board. And the thing to note here is that along the edge, they're all dead. They're all 0. And then I have the sort of random values in here. It should be about 50% dead, 50% alive. So that's our initial state of the board. So now that that's set up, let's get the handler stuff set up, the sort of tick set up here for us. So we're going to make an event handler, action event. And I'm just going to call it handler. So we've sort of done this many times here. Let's make sure to import these. Let's see here, JavaFX, and I spelled it wrong, so that's why it was. And then also JavaFX. This is going to be a new event handler, action event, and then I'll put my curly brackets in, semicolon, and then I'm going to press enter here to give myself some space. And then I'll hover over and say add unimplemented methods. And the only thing that this needs to do is call update game, and we're going to send in the board and my grid pane P, which I think I just named P up here. Yes. So I just need to send in my board and my grid pane and call update game. So the tick that's happening here is going to be doing this setup here. So this is where we're going to apply the rules and do any sort of update stuff that we need. Lastly, we need to do the timeline stuff to actually create our tick properly. So this will be timeline. I'm just going to call it T equals new timeline. And then we have a new keyframe. And then in here, this is the duration dot millis. And we'll put it in here. This should be relatively long because we don't want it to go too fast. Otherwise, it'll be tough to sort of see what's going on. So maybe something like 250 milliseconds, like a quarter second per frame. We can always adjust that later. And this will be the handler that we send in. Of course, duration is going to need to be imported. It sort of automatically did that when I selected millis, so it ends up here. But I do need to import keyframe and timeline. And then lastly, I'll do t.set cycle count, and we'll do timeline.indefinite, and then we'll say t.play. So that gets that going for us. Right now, of course, this isn't really doing anything. If I run this, it's running, it's doing everything properly, but nothing's changing because we haven't coded up any of that stuff yet. So I'll go ahead and close it. Now we got to deal with this. So the big thing to remember here is that inside of our start, we're just setting up the board. That's it. So it's similar to the sort of initial stuff that we did for the 1D version. Not a whole lot of setup we have to worry about. We are creating a random number generator. We're doing all the action event stuff that we need, so it's a little bit more complicated. But in the end, it's still just messing around with the board. Now, there is one key aspect of this when we do the updates, and I'm actually going to not put it in first. I'm going to code it up sort of naively first, and then show you what happens if we sort of do it incorrectly. So there's a couple ways to do this this sort of inner part here, because what do we need to do? We need to count all the neighbors, all the neighbor values, 0 or 1. We need to count them up. If it's 1, then it's alive. If it's 0, then it's dead. So if we count all the neighbors, we look at those 8 cells around, then we count them up, we know how many alive neighbors we have. So I need a value called sum. I'll set it to 0. So for each center cell, that's what this is picking. Board ij is a center cell. I'm gonna create a variable out of that. This is gonna be center. This is gonna be board ij. That's the center cell that we pick. And this should be, we need to get the state from this one. So this is the center state of our cell. It's either going to be 1 or 0, but that that determines if it's 0, then we might have a birth. If it's 1, then we might have a death. So we need to know what that state is. Now we could code up each individual one here, right? Because we have 8, so I could do something like, let's say we do something like upper left equals board dot or board and then a couple values and then get state. We have to think about what these are. We're going up 1 row. So what does that mean for our rows? It's I minus 1. We're going to the left 1 column. So that's j minus 1. So that's our upper left. So then you can imagine there's going to be every single possible combination of this, 8 more of them. So that's a lot to think about. This is very easy to sort of mess up. So maybe we have center left, and then right left or whatever. Or I guess we'd have upper right. So we'd have center, call it like upper center. There we go. So upper left, upper center, upper right. We would just have say center left and center right, and then we would have lower left, lower center, lower right. And then we would code up sort of all the individual numbers here. Now, you can do this. I'm going to put it in here like this, but then I'm going to show you the sort of other way to do this, probably ultimately the sort of better way to do this, or at least sort of a loop way to do this, so you don't have to sort of think about each one of these values. So upper center, it's the same column, but up 1 row. Up 1 row. Upper right is going to be the same, up 1 row. Actually, let me do, hold on. This should be, yes, this should be fine. So up one row to the right 1 column. The center is going to be the same row, but to the left 1 column and to the right 1 column. The lower will be a plus for each one of these. So plus 1, because we're going down 1 row. And then to the left will be minus, center will be the same row, and then right will be this row. And all I have to do is add all these together. So sum, so say plus equals upper left, upper center, upper right, center left, center right, lower left, lower center, lower right. And that's the sum of my neighbor states. Now, if you wanted to do this with loops, I'm going to write the sort of loops in here and then I'll comment them out afterwards. So we'll sort of keep it like this. If you want to do this with loops, take a look at how our i's and j's are changing. We've got -1s, we've got basically 0 here, and then we've got +1s. So we could actually write something like this. I could say for, and let's use like x and y. So I'll say int x equals 0, x equals -1. We're going to use x as these values. -1, x less than or equal to 1, because we go from -1, 0, 1, x plus plus. And then we have to do this for our j's as well. For our j's, we have a -1, a 0, and a +1 as well. So I can say for y, for int y equals -1, y less than or equal to 1, y plus plus. So inside of this loop, we would be able to get all of these values. We basically would say something like board I plus x, j plus y. That we'll do like get state, and we would do something like sum plus equals this. Now this also gets the center state when they're both 0, so we'd have to subtract that value off at the end of these loops. But this is a way to do this sort of setup that we have here to get all of these states and add them all together. So relatively easy to do with loops and much more compact, but this way here might be a bit more intuitive to start with. But I do recommend looking at this sort of loop way. So I'm going to leave it here, just comment it out. All right, so we have our sum. So now let's apply the rules. So let's do deth first. So if center equals 1, and then we'll have else if center equals 0. Actually, yes. Let's do. Let's flip that around. We'll have deth first, and then we'll have if center is 1 after that. So we have sort of a situation where the center is dead, and the situation where the center is alive. All right. So inside of here, and we're going to have some nested sort of ifs here. So there's sort of more compact ways to do this, but I want to try to make this hopefully as intuitive as possible. So if we're dead, the only way we change back to alive, the only way we actually change the value is if sum, that's our neighbors, if that's exactly equal to 3. Then we can say board ij dot set state, we come back to life. We're going to change it to a 1. So hopefully that makes sense. If we're dead and there's 3 live neighbors, change us back to life. And that's it. Otherwise, we stay dead. That's the only way to change your state. If you're dead, the only way to change your state is 3 live neighbors. So that's a relatively easy one. If we're alive, there's a few more sort of conditions here. If we're alive and the sum is greater than or equal to 4, or the sum is less than or equal to 1, so this is overpopulation or loneliness. Then we change our state. Set state 1, 0. So we die. So this one here has got a couple conditions: greater than or equal to 4, less than or equal to 1, then we die. Otherwise, we stay alive. If there's 3 or 4, if there's 2 or 3, then we stay alive. We don't bother changing what the center, what that center one is. But I want to throw in something here that might look a little bit weird to start with, but it's going to be important when we go in and change our stuff. So when we go in and actually change this, because this is not quite going to work the way we expect. I'm going to throw an else in here, and the else is just going to be board ij dot set state 0. So you sort of think, well, it's the center's already 0, so why bother doing the set state again? You'll see why in just a couple minutes. So ij dot set state 1. So I just want to have the ability in each one of these if else's to make sure that I'm changing the state either to 1 or 0, depending on the situation. So let me actually go ahead and run this. We should be pretty close to doing something interesting here. And it was, let me increase the size of the window here so we can sort of see it to start with here. Up here, let's make this, let's say we got 100, each one's what, like 5 or something. So maybe we'll start with like this and see how big this is here. So everything just sort of starts and then sort of goes away, which is, maybe a little bit weird. And then everything's gone. So we're going to have to see sort of what's going on with our setup here. Let me put, I'm going to put a couple more here. Yes, I should have this outside of, let's see, should be outside of there because these are our two if statements. This is the end of I, this is the end of J, and this is the end of rules. Just so we know what we're looking at when we see these, and this is the end of update. All right, so we get some weird sort of behavior going on. And one of the things that I want to mention, any cellular automata, you need to do this. The thing I'm about to describe. Any cellular automata, you have to have a place to read from and a place to write to. So for example, if I have some grid here, and I read from this grid, so I'm looking at this one here and I read all these guys around. If I write to this one, if I change what this one is, and then I move to the next grid location, and I look at this one, I've just changed the one previous to it. So it's not the same as it was to start with. It's not the same state of the board originally as what I'm now looking at because I just changed it. So I'm sort of, if you sort of think of the Photoshop blur that we did, I'm sort of blurring a pixel and then reading that blurred pixel and then doing even more blur on the next pixel based on the one I just blurred. So what you need in any cellular automata is you need two boards. You need one that you read from. So I'm going to look at this one. I'm going to read these values. And then over here on this sort of temp board, so this is, say, our board. This is our temp board. I'm going to read from this one, and then I'm going to write whatever the result is over here. Maybe it changes to a 1. So I'm going to read from the board, write to the temp board. And then after I'm all done, and I filled in this temp board, I'm going to copy this temp board back and fill up the board. So there's going to be a copy here. Any cellular automata, this is what you have to do between iterations because you don't want to change the state of the board as you're reading from it. You want to keep this static and only write to a temporary board. That's why I've sort of set this up here because we're going to change this to temp in just a moment. Now there's some performance implications here if we sort of have a super large board the way I'm going to do it, but just in our sort of update game function, I'm going to do the same sort of thing that we did up here at the top. I'm going to create a temporary board, and I'm going to basically fill it with cells. So I'm going to copy those lines there. And then at the top of our update game, I'm going to create a temporary board. And in here, I'm going to fill it with cells. It has to have the cells, otherwise our get state and stuff isn't going to work, or our set state isn't going to work. So that's all I did. Create a temp board, fill it up with a bunch of new cells. We still use get state, so this is where we're reading from our board, but we're going to write to temp. So we're writing the temp. And then the last thing we do is copy all the temp states to the board. So again, I need to go through all of my iterations here. So every single cell that I've sort of gone through. Actually, so this needs to be at the very end, not at this point. So after my IJ, then we copy all the temp states. We've gone through all the temp stuff to the actual board itself. So in here, I'm going to say board IJ dot set state temp IJ dot get state. So I'm going to set the state of the board at IJ equal to whatever the get state of the temp board is. So we have these two boards that we're working with, these two sort of array of cells, these 2D array of cells, setting it in temp, reading it from board, and then at the very end, right before we're done with the function, copying all that temp stuff to the board. You have to do this. This is one of those little sort of complications. It's sort of easy to miss when you're just sort of coding something like this up. All right, so let's see. And the reason why there's a little bit of a performance implication here is because I'm creating all these cells every single time I update the board. In principle, you would only do this once up here in the main program, the same place I create the actual board, and then I just send it into the function rather than creating it every single time. So potentially there could be some issues there. Performance-wise, but it shouldn't be too impactful here. Now, we're still getting them to go away, so there's probably something wrong with a rule that I have in here somewhere. So let me check what we have here. So we've got those. Changing it in temp. Check our board here as well. Check our getting the states, because if we have one of these wrong, which is one of the sort of reasons why it's useful to use the loops rather than sort of code these up, because if one of these is wrong, then potentially there's sort of major issue that's not necessarily easy to find. Let's see. It's possible it's happening here as well. So if we're dead, then we come back to life. If we're alive, then we die. It's here. This should be greater than or equal to 4 and less than or equal to 1. I think that's where the issue is. I probably said it right, but I probably used the wrong one. So there we go. There we got some more sort of interesting stuff happening. So we might make this a little bit faster. I think that was actually the only issue here was my stuff there. Might make this a little bit faster, but you can see some of the blinkers. We go from horizontal, there goes from vertical to horizontal, and then back. We have some of the blocks here. There's actually a glider that was over here on the side, just for very, very briefly. Let me go ahead and speed this up a little bit. I think 250 was a little bit slow. So up here, I'm going to go to 100. Go a little bit faster. There we go. So now this looks a little bit more interesting. We have a few sort of static shapes. You see the blocks and stuff in various places. And yeah, this will just keep going until it gets to a steady state. You can just sort of see it sort of moving around and stuff. And there might be a glider here and there, it depends on if we get, there was actually a glider that showed up very briefly. So there's one right here. Here's a glider. And then then hit something and it disappears. So again, this will just keep going, but you can see some of these. There's some loafs, there's some beehives, there's the blinkers. That's mostly what you see when you just start with a random board. But yeah, that is a game of life. It's relatively easy to program up. That's one of the cool things about this. Is it's not too complicated, but you do have to sort of think a little bit about that sort of extra board that you have, the boards you read from and the boards you write to. And then sometimes you have to think about, I mean, obviously I had a little error there with my less than or equal to's, but in the end, we get exactly what sort of Conway was envisioning here. So hopefully this was at least sort of somewhat interesting for folks. It's a relatively common thing to see in a CS1 or a CS2 class because it's sort of easy enough to program up because it's just a couple of arrays, and then trying to apply a couple of rules. Even I think in the CS1 class that I was in, it was a C++ class, but the professor had coded up the graphic stuff. So it was all like OpenGL and stuff. So professor had coded that up for us, and it was sort of we had the code, and it was just like, don't touch the code below this point, and then we had to code up the rest of it, basically using the classes and stuff, and then coding up the rules. So this is sort of similar to that. Imagine if this was like a homework assignment, and I did some of the JavaFX stuff for you, where you had to go in and code the rules. So that's the idea of Game of Life. You could code up some extra stuff here if you wanted to, make it so when if you press spacebar or something, it resets the board to a random state or something. So there's a bit more you can do to it. But really, in the end, it's not a whole lot different than the 1D version. It's just now we have to use that handler, the event, the action event stuff to update the actual visuals every single frame, and really just give our board a random values. Make sure we create a temp board. Look at what all the neighbor states are, add them all up, either by just manually coding it or by a loop, and then applying our rules. And at the very end, applying our rules to the temp board, and at the very end, using the temp states and setting all of the board states. And that's it. So hopefully that was sort of somewhat interesting. And there's lots of cool things that you can do with this. Let me go back to the slides because we're not quite done. I didn't pull up that video that I mentioned from last time. Let me see if I can do that real quick here. If I remember where it is, so I can show you one of the fluid videos as well. All right. So yeah, so CA is not just for the sort of simple sort of game-like behavior. You can do more sort of sophisticated things with it. So as an example, and this is the video I'm going to show you. You can do fluid dynamics. The HPP model is the one that I sort of have working at the moment. It's very simple. The rules, all the rules are right here. There's only 4 rules. If you have a little fluid particle and nothing else, it just moves through each grid point. If you have 2 fluid particles like this coming to an intersection, they just pass through each other. So if they come at 90 degrees, then they just pass through each other. If they come head on, then they sort of bounce off of each other at a 90-degree angle like this. And then if you hit a boundary, so say this was a boundary right here, then it just bounces directly off the boundary. That's it. 4 rules. Less rules than Game of Life. But what you come up with, and I have a little sort of video like this that was from Wikipedia, but I have actually a better one that this sort of shows them just four sort of fluid particles hitting stuff. So you can actually go watch that, I think, on Wikipedia. But I have a version of this. Let me do one of these here, like this. So I've put little arrows on there to show the sort of magnitude and direction of the flow. And you can sort of see the underlying grid here as well. But the point here is, even with that sort of square grid underneath, you start to get these wave-like behaviors. And so what you'll see is you'll see these sort of wave structure. It's just moving through, and then it's going to like bounce off the edges. So up here, the sort of ones that hit the top is going to sort of bounce off. And all this was sort of like imagine it if you've ever messed with like a wave chamber or something before. It was just a sort of large amount of water in a square up here at the top, and sort of a lower amount of water everywhere else. And that's why we got this sort of wave behavior out. And so, yeah, so this will go and the waves here will bounce off and start coming back. And so you'll see the arrows again are sort of giving you the direction of technically it's a sort of momentum of the liquid at those individual points. And yeah, so this will bounce off, and then stuff will start to sort of come back this way. The colors represent sort of the amount of water, the density of the water at the location. So right now you can see the wave is sort of this sort of more water here, less water in these areas, but we have a lot of momentum now moving sort of back this direction. So you start to get this sort of cool sort of wave-like behavior, even on a square grid with only 4 rules. That's one of the impressive parts here. Let me show you that initial state again. So here's the initial state. So the initial state is just a cube like that. So the water moving up this way is going to be bouncing off here. So in here, sort of the darker blue, less sort of liquid there because it's starting to sort of expand outward. It bounces off of here and then starts to move back that way. So you see some nice sort of fluid-like behaviors in a very simple grid, very simple cellular automata. And it's the same thing. It just has some rules that you apply every single frame. So this is called the HPP model. The HPP itself is just the last names of the 3 guys that originally developed it. There's also a more complicated one, the FHP model, where you actually have a hex grid. So you have sort of 6 directions, and this is it. This is the rules for what's known as the FHP1 model. You have a rule here, and then you have a probabilistic rule. So if you have 2 particles that come head on, they'll either reflect this 60-degree angle or this 60-degree angle from the direction that they impacted. Then there's like 3 particle collisions and stuff like that. So in this case, there's actually only 4 rules for this one as well. They're just a little bit more complicated to consider. So this is one of the FHP model. You get some more interesting stuff. I don't have a video of that. I have a picture here that shows these sort of vortices that form. So you have a little barrier here, and you have some flow coming in from left to right. And with the barrier here, it causes these little sort of vortice things to form. So there's some interesting stuff to do with this one. More complex fluid behavior than HPP because there's more rules, and it's a hex grid rather than a square grid. So fluid dynamics, a cool thing you can do with cellular automata. Force fire spread, very interesting as well. You can come up with a lot of different types of scenarios for force fire spread, and you just code up some rules, right? You say, all right, does fire have an easier or harder time going, say, up in elevation? Is there wind that would maybe sort of preferentially sort of force the fire into a particular direction? All those sorts of things that you can think of in sort of the physical world, you can apply as rules to something like this, something like force fire spread. There's lots of others as well, things like sand dune movement across a desert, snow accumulation, predator-prey model. For the snow accumulation one, I published a paper with a student in a video game journal about basically cellular automata for granular media. So things like sand or snow or stuff like that. It was a probabilistic model. So there's some cool stuff you can do with that, and people are still doing those sorts of things. Predator-prey model, disease transmission, it's particularly relevant these days. Fractals, obviously we created a Sierpinski's triangle last time with the 1DCA, so you can do other fractals as well. Heat diffusion, traffic simulations, all kinds of stuff you can do with cellular automata. So hopefully these 2 lectures are at the very least sort of fun, but also show you a little bit about how to use some more of the JavaFX stuff and a little bit how to mess around with classes and arrays of classes or matrices of classes. That's sort of mostly my intent here, but it hopefully in a more fun way than just some dumb examples in a lecture. So that is all that I have for you today related to Game of Life. Not sure exactly what we'll do next time. I'll have to think about that. But yeah, that is it. So I will see you guys in the upcoming week.